Bismillahirrahmanirrahim. Assalamu alaikum and welcome to this session. In this session, we are going to talk about queues, the same everyday phenomena that you encounter when you go to the supermarket and you encounter a waiting line. And you have to wait in that line to get to the cashier so that you can pay and leave the system. Why would it benefit us to understand how queuing works? The answer to that is that a queue or a waiting line is a very good system to model a shared resource. And in fact, queuing theory is an entire discipline, which is queuing theory is a kind of analytical modeling technique in which we use applied probability models to characterize some empirical process. And then we would see that systems typically have stochastic arrivals and placement of demands. And because of that, even if the average arrival rate of the customer is less than the average service rate of the system, still we can actually have formation of queues. And how is that relevant to a computer network? As was already earlier covered in this course, we can think of a router in which the packets are arriving. Now, the link on which it would be exited has a certain rate. But what happens if we have a transient overload? That is, while still the average arrival rate is less than the average service rate, still it may be that for some instantaneous time, the instantaneous arrivals are more than what can be serviced by the system. And in such circumstances, it is helpful to buffer the system or to make a queuing line so that when the system becomes available, then we can actually give the customer to the system, which can then service it. And because of that, we will not be losing a customer. Queuing theory is a very diverse topic which applies to many different areas. It applies to business, it applies to operational management, it applies to logistics, and it applies to computer networks. Because in computer networks, like in all the other systems, we have shared resources. And if we have a shared resource, and when we have many users which can demand access to this shared resource, it may be that many users demand access to the shared resource at the same time. And because of that, we would have the formation of a queue. For a system to perform well, we require the queue to be of a relatively small size. The average waiting customers in the queue should be relatively less. And also the average delay should be less. We would see that it is actually very helpful to study queuing with mathematical tools, because in many cases our intuition would fail us, and using formal mathematical tools we can analyze the system and come up with performance metrics. So for example, we can model the arrivals to a router by an ideal probability distribution, and then we can use mathematical tools to analyze the system and get performance metrics. And these would be in a stochastic or a probabilistic sense. So we would have some expected values, and these are very valuable for us because they provide intuition of how the system would work if certain conditions are changed. And they also give us approximate answers. And on account of both these reasons, it is very useful for us to study queuing theory. One may ask a question that why do we actually need to recourse to have queues? Why can't we just have systems in which we have such high capacity that we don't need to form queues? So we will actually answer that in the duration of this session, but a brief answer to this is that if we have a deterministic queue in which everything is coming according to a set pattern, then in certain cases we can avoid queues. But in real life scenarios, the arrival of customers do not follow a predetermined arrival pattern. So there is no deterministic arrival pattern. And whenever you have stochastic or randomness in the arrival pattern and in the demand of how much of the resource is wanted, we would see that even for very lightly loaded systems, we would still have sometimes queue forming up. And because of that, one thing that needs to be understood is that if you want to completely eliminate queues or make the chances of the formation of queues very small, we would have to over provision the system. We would have to place a lot more capacity than is needed in almost all the scenarios. So for ensuring economical resource sharing, it is beneficial to have a queue, and then according to the arrival pattern, we can provision how many servers or how many entities that will service the customers are to be placed. So with this introduction, let me now outline how I'm going to treat this topic in this session. Initially, I'm going to talk about the history of queuing theory, how queuing theory was born, how did we actually come to analyze a waiting line mathematically, and what results did we have at that time. Queuing theory is almost 100-year-old, so we'd be tracing the roots or the history of this theory, how it came about. Then I'm going to talk about intuition of queuing systems, because queuing theory is a mathematical subject. It's a mathematical discipline, and we can get lost in details and in the formulas for describing stochastic processes. But one thing that we can use to gain a lot of intuition is to analyze realizations of these stochastic processes. So we would take some sample parts of how this stochastic process may play out in real time. So we would be considering examples, and we'd be seeing some principles that about the operation of queues. So we'd be learning many things in an intuitive manner in this portion of today's session. And finally, I'm going to talk about how can queuing systems be classified, because queuing theory is almost 100 years old and we have a lot of results now. But if we want to refer to the kind of queuing system that we have, we need both a notation and we need to know what different characteristics of the system do we actually have to take note of. So that would be the final part of today's session. I start with the history of queuing theory. So queuing theory basically started in the early 20th century, around about 1909. And it was started by an engineer in Denmark known as Agner Erlang. And his interest was basically in provisioning resources for a telephone network. So let me make this more concrete. His work was essentially that given a certain population and we want to connect the exchange that is servicing that population to a long distance exchange. So we have to connect this exchange to another exchange. The question Erlang thought over was, how many trunk lines do we need to have? And this is a very important question because it has consequences for all of our study that we'd be doing in queuing theory. So to make this example more concrete, let us give some numbers. So imagine that there is a population of 100 telephone users. So there are 100 telephone users, and then we want to connect the exchange which is servicing these 100 users to a long distance telephone exchange. So for this system, how many trunk lines do we require? So let us think of the different bounds. On one extreme, we can think of connecting the local exchange with the long distance exchange by a single line. But that would mean long waiting lines and also blocked calls, because at any given time, we can only have one ongoing call. So this is very restrictive because we would have many blocked calls. Every time someone wants to call, if one person has gained access to the trunk line, they would always get busy tones. So what can we do else? In the other extreme, we can actually have a single trunk line for every user. So in a sense, we are provisioning for every user being active at all times. So in this sense, a user will never have a busy tone because we have enough trunk lines to support all of the users all of the time. But this is clearly wasteful in the sense that you are placing more resource than is necessary. And the question of business considerations arise because we don't want to put money where it's not required. We want to provide good service, but also in a cost-efficient manner. So we need to find some trade-off between these two extremes to find where we want to operate. And to actually answer that, an observation which is straightforward now, but was not considered in the time of Erlang, was that we need to consider that all of the 100 users are not going to use the network all the time. So we can actually, instead of thinking about peak performance in the sense that worst case everyone comes and is active all the time, we can think about average demands of the users. And if we can characterize the average demand placed by all the users on the network, then we can actually do better than these two extremes. So let's imagine that we did a measurement exercise and we determined that there are on average 5 calls per hour received by the telephone exchange in the busiest hour. So we're going to provision for the busiest hour, because if we don't consider the busiest hour and if we take the average number of calls during some off-peak hour, then we run the risk of having lots of blocked calls in the busy hour. So we take the busy hour and we take the average number of calls received in that busy hour. So we're assuming that this is 5 calls per hour, and furthermore we are also making a simplifying assumption that all calls last for 1 hour. So in that sense you have 5 calls per hour and each call lasts for 1 hour. So all in all, it seems like we would require 5 trunks. In terms of teletraffic and in the terminology they use, this amount of traffic would be called 5 Erlangs. So now the question is that we know that on average there would be 5 calls per hour and each call would be active for 1 hour, and therefore we would have 5 Erlangs. It seems to make sense that we should have 5 trunk lines to service this population of 100 users. So what do you think? Should we have 5 trunk lines? The answer to this, of course, is that no. And this was answered emphatically by Erlang, because he showed that even if we cater to the average number of calls per hour and we budget the number of trunk lines according to that, calls bunch up, in the sense that the calls are not going to be distributed in a deterministic sense. So it may be that in some cases you would have no call coming at all. So there is a probability of that, because the number of calls in any given hour is distributed according to the Poisson distribution in Erlang's model. So because of that, in some cases you will have no calls at all. In some cases you would have 1 call. In other cases you would have 2 calls, 3 calls, 4 calls and 5 calls. When we go beyond this, and there is a probability of that happening according to the Poisson distribution as shown on the screen, you can see that if you have 6 number of calls, then what will happen? 1 call would be blocked. It depends which 5 calls get into the system, and the 6th call would be blocked because there is no space for the 6th call. So one major insight provided by Erlang was that this average number is actually just an average. It is just a model of what the distribution is like. But the distribution is not centered on just the expected value. The distribution also has other possible values, and they can also occur. And because of that, when you have calls bunching up, you run the risk of having many calls blocked. So then next question is that if we fix the number of blocked calls that we can accept, can we determine the number of trunk lines that we need to have? And Erlang showed that this can be done. And in fact, we're going to answer this question for traffic of 5 Erlangs. And we're going to develop this further in the course of these sessions on queuing theory. But we have a table known as Erlang B, which basically deals with this, the probability of blocking. And you also have the amount of traffic, and you also have the number of trunk lines that are needed. So if we have a traffic of 5 Erlangs, and if we are only happy with a blocking rate of 1% or less, then we actually need to have 11 trunk lines. And this can be seen on the slide. You see that you require 11 trunk lines to provide service to 5.16 Erlangs, which would cover our case in which we require to service 5 Erlangs of traffic. We can have a look at another graph, and this would be understood better when we actually discuss the different queues in more depth. But you can see a graph in which we have steady state probabilities for a finite capacity queue, because in this case we have finite capacity. In the case that we've just determined that we require 11 servers to service the 5 Erlangs traffic that we have, we would see that you would have a probability distribution. And because we have 11 servers, what is the probability that we would have all these 11 servers busy? And I will not answer how this graph is actually created, but we can see that the probability of having 11 customers in the system is close to 0.01. And when we are in this state, we will not be able to accept more customers. So this actually also complements the other table that we can see on the slide. Okay, let's now move ahead and talk about queuing systems in an intuitive way. We want to analyze how queuing systems work by seeing realizations of stochastic processes that represent queuing systems. So first of all, let us consider the simplest queue that we can consider. This is a deterministic queue in which the customer arrivals and the service times are both deterministic, in that you would have arrivals coming after exactly 1 minute. So inter-arrival time is exactly 1 minute. And the service time, which is how long does the server take to service a single customer, that is also exactly 1 minute. If you have such a system, we would see now how this system would play out in time. So we start at t is equal to 0. At t is equal to 1, the first arrival comes. And because of that, we have one customer in system. That customer is not queued. So you need to understand that we can talk about customers in system and customers in queue. So those customers that are in the queue are actually waiting for service. While when we talk of customers in system, it includes both the customers in queue and also those customers receiving service. So in this case, the arrival comes and then we have immediately one customer in system obtaining service. After exactly 1 minute, this customer would be serviced, and then exactly at the same time, we would have another arrival. And because of that, this pattern would keep on going, because this is a deterministic pattern. And if we inspect this queue over time, we would see that no queues are formed. And in fact, a customer comes, it obtains service, and when it goes exactly at the same time, another customer comes. In general, when we talk of deterministic queues in which both the arrival patterns and the service times are deterministic, then it suffices to just ensure that the arrival rate is less than the service rate. And if that is the case, then you would have a system that is stable and there would be no queues formed. So this is very good from the perspective of performance. But from the perspective of being a good model of reality, this is not so good, because typically the arrival patterns are stochastic and they are very, very rarely entirely deterministic. And similarly, the service times. And because of that, this just has pedagogical value, that we can talk what will happen if you have deterministic arrivals and service patterns. A more realistic example is when you have a stochastic queue in which the arrivals to the queue are random, and also the time it takes to service a customer is also random. So let us consider an example where the mean arrival rate and the mean service time is exactly the same as was the case in the deterministic example. So we have inter-arrival times as either 0.5 minute or 1.5 minute with equal probability. And if that is the case, the expected value is 1 minute. Similarly, the service time is exactly the same. it will be either 0.5 minutes or 1.5 minute with equal probability, and therefore the expected value would also be 1 minute. So this is interesting. We can compare both the deterministic queue and the stochastic queue because the enter arrival time and the service time are exactly the same. So what happens in the stochastic queue? So the red crosses actually represent arrivals and the blue circles represent departures. We would see that in this system we have formation of queues because in the middle part of the graph we see that there are multiple customers in the system where the first customer would be obtaining service and the rest of the customers are queued waiting for their service. So how has this come about? For the same mean enter arrival time and the mean service time, we saw that there were no queues in the deterministic queues, but now we have formation of queues. And wait for it, this queue not only has queues, but it can be shown that the queue would actually be unbounded in the sense that if we keep on inspecting this queue over time, the mean number of customers in the queue would actually increase and it would keep on increasing, and the expected value of this is infinite. So this is seriously against our intuition because we would expect that if the enter arrival time and the service time are the same, things would be similar. But we see that if we have a stochastic queue, the randomness in the arrival and service patterns actually make the queue more tricky in the sense that now a performance would not be as good as it was in the case of a deterministic queue. This, by the way, is also the message Erlang gave us. He also said that when you have stochastic arrival patterns, calls will bunch up, and because of that you would have situation where your queue would operate in a manner which does not entirely go along with our intuition, and it does not match with what will happen if we have deterministic queues. We can have a look at the stability of queues, and I've just mentioned that in the case we just saw where we have a stochastic queue and the enter arrival time and the service time are exactly the same. If you have that case, we can actually show that the expected value of the mean number of customers in the queue would actually go towards infinity as we keep on inspecting the queue over a long period of time. We can also now define a new notation in which we define rho as the ratio between the arrival rate and the service rate, where the arrival rate is represented by lambda and the service rate is represented by mu. So for stability of stochastic queues, we require that this rho should be less than 1. When you have a single server queue, then this rho should be strictly less than 1. If that is not followed, we would shortly see that you would have unbounded growth of queues. So let us now inspect how the queue works for different values of rho. And one important point here that I would like to point out is that the behavior of these stochastic queues is more dependent on the value rho, which is the ratio of the arrival rate and the service rate. It does not really depend on what the precise values of the arrival and service rates are. It depends on their ratio. And for all systems that have the same value of rho, from the perspective of queuing theory, they are almost the same. And in fact, they would give the same performance measures. Okay, let us now inspect the queues for different values of rho. So initially we start with a lightly loaded queue. And now let me define the arrival process distribution and the service distribution. Earlier in the example we saw we had a funny looking distribution in which you could only take two values, either 0.5 minute or 1.5 minute with equal probability. In queuing theory, a more traditional approach is to model both the enter arrival time and the service time distribution by exponential distributions. And this is actually very useful because exponential distribution has the memoryless property. And because of that, analysis of queues having exponential distribution becomes very easy, because as you recall, when you have a Markov process, the time a process spends in a state is also exponential. So taking into account all of these factors, most of queuing theory is actually based around the exponential distribution, modeling the inter-arrival time and also the service time. In the case that you can see on the screen now, you see that the value rho is relatively less. It is just a value of 0.1. So we are assuming that we have a Poisson arrival process having a rate of 0.1 arrivals per minute. So this is the mean rate that you have. Exponential service tells us that the service time is exponentially distributed with a mean rate of 1 departure per minute. And if we take the ratio, we get the value of rho, and that is equal to 0.1. Now let us have a look at the instantaneous queue length as we see the time evolution of a queue. So we see that most of the time this queue is empty, or this is idle. And this is precisely how queues that are working well should be. Most of the time they should be idle. And if that is not the case, we would see that our system is not performing very well. Because one thing that you must understand very well is that queuing is not a permanent solution. It is only designed to cater to transient overloads. And transient overloads by definition are just fleeting overloads. So the overload would come for some time and then it would go away. On average, the service rate should always be more than the arrival rate. And if that is the case, you would have a stable system. In this case, when we have rho is equal to 0.1, the service rate is significantly larger than the arrival rate. And because of that, most of the time, we would have the system idle. You would have a customer coming in, and because the service rate is high, you would immediately service it and come back to the default value of being idle. So this is a system in which we have good performance, but one thing that we must observe here, that even for such low utilization, we still have formation of queues. So you would see that sometimes you have queue lengths going to 2, which actually tells us that there is a customer in service and there is also a customer waiting. Why do we have a customer waiting when the utilization is so low of the server? The answer again is that customers bunch up. It may be that for a long time no customer comes, and then 2 customers come at the same time. And because of that, we cannot completely avoid queuing. So this is another take-home message, that when you have stochastic arrivals and stochastic service times, you would occasionally have queuing even when the system is very lightly loaded. So if you want to make a system that does not have queuing at all, you would have to ensure that the server is very, very poorly utilized. And that in an economical setting, or when we take into account the business aspect of it, becomes inefficient. Okay, now we can talk of a moderately loaded queue. A moderately loaded queue is where approximately the arrival rate is half of the average service rate. And when you have that as your setting, you would see that now queuing is more frequent. You would often have customers coming in, and when the customer is in service, you would have other customers coming in. So you would see that you have even queue lengths of 4, which means 1 getting service and 3 waiting. And you also see that most of the time the system is busy. So approximately half of the time the system is busy. But for the rest of the time, you would see that the server is idle. This is very important. This is a good way of analyzing the performance of a queue. Does it get idle or is it always busy? So in this case, it is busy half of the time and it is idle half of the time. And from the instantaneous queue length, we can actually calculate the mean queue length. And that is one performance measure that we have for quantifying how well the queue is performing. When we have the value of rho go towards 1. So we have a heavily loaded queue where now the utilization is reaching 100%. So this is the danger zone. If you see how this stochastic process plays around in time, we would take one realization of this, and we see that the number of customers waiting in the queue is actually growing over time. Why is that the case? Because if we have rho is equal to 0.99, that actually tells us that arrival rate is less than the service rate. It is equal to 0.99 service rate. So if that is the case, it really boggles the mind and it defeats our intuition that if on average the service rate is more than the arrival rate, then why do we have unbounded growth of queues? And the answer to that is that, again, calls bunch up. And because of that, you would have bursts coming up. And the other important aspect of this is that the system, when it gets idle, it cannot give service to anyone. So at those times, the server does not get any credit later on for having this idle time. In other words, a server cannot give service to a customer before it has arrived. So while the arrivals are not stopped by anything, the service is automatically stopped when you don't have any customer. And when that is the case, you can imagine the server being idle for a very long time, and because of the average, you would have now a big burst of packets coming in, but the server can only service the packets according to its defined service rate. And because of that, the queue length would, grow very large over time. So this is a very important insight, that any queuing system cannot be operated at full utilization. And when you have a queue that approaches full utilization, you would have the mean number of customers in the queue, the average waiting time, it would just grow very fast. And in the case where you have 100% utilization, in the asymptotic case, both these values of average queue length and average waiting time goes to infinity. So this actually tells us that we should be operating our queuing systems or our shared resources in the area where the utilization is close to 0.7, because beyond that point, the performance worsens off very, very rapidly. We will see this in more depth when we talk of the queues in future sessions. Now let us talk about classification of queuing systems. And to build your intuition regarding this, I will talk about everyday queuing systems, and then I would relate it to queuing systems as they are known in queuing theory. So let us start first of all by the simplest of queue, the kind of queue you would face if you go to your local grocery store. In that grocery store, you would have a single cashier, and he would be idle most of the time. And when the customers come in, he would be servicing them. But as is typical, you would have multiple customers come in at the same time, and when a customer arrives and he wants service and the server is already servicing some other customer, this customer has to wait. So we can represent this system by a single server queue, because there is only a single server and everyone waits in a queue to get service from this server. So there are some things which we have not talked about yet. For example, how large can the queue length be? Typically in a shop, the queue length would be finite. It cannot grow larger than the size of the shop. But in queuing analysis, it is more common for us to actually assume infinite buffers. Also, another point that we may consider is that the customers are arriving to this system, but what is the population from which these customers are coming? This is important because it may be that if you have a finite population and all of the population, or most of the population is already in the system, then the arrival rates would generally reduce. So if you have 50 people in the village and they all go to the grocery store, if 40 people have already come into this grocery store, then the arrival rates would understandably reduce, because there are fewer customers from which the arrivals may come. But if we consider an infinite population, we can actually model the arrival by a Poisson process. And Poisson process is a process in which the arrival rate does not depend on how many customers you have already in the system. In other words, a Poisson process is state independent. So this was a very simple example of a single server queue, and in this we just said that when the server is already busy, arrivals are queued. Let's make this a little more complex. Imagine a big supermarket now. In a big supermarket, typically you would have multiple cashiers, and for each one of the cashier you would have a separate line. We can represent the system by having multiple single server queues. So for each cashier, since there is a separate queue, you would represent that by a single server queue, and because there are multiple servers, we represent this entire system by multiple single server queues. So the example as mentioned is a large supermarket with multiple cashiers, in which, this is important, every cashier has its own line. We can actually do better than this system with the same amount of resources, and we can do better by having instead a separate line for each cashier. We can have a single line that feeds to all of the cashiers. This is represented on the screen now, and we call this a multiple server queue. The distinction of this class of queuing system from the previous class is that in this you have a single queue that feeds to all of the servers. A familiar example is when you go to the bank and you take a ticket, a waiting ticket, and it does not depend, you're not tied to a single bank teller. Whichever of the bank teller gets available, you would actually proceed to that teller in the order of first come, first served. This is another important specification of a queuing system. How are the customers that are already in the queue treated? Do we have a first come, first served basis treatment, or do we have some other queuing scheduling? So the idea here is that whenever you have human customers, then typically we always have first come, first served, because humans have a very strong notion of fairness. So the customer who goes in first typically wants to be serviced first. And this is another benefit of a multiple server queue, in which a single queue feeds all of the servers. Because in this case, you will never have a scenario in which a customer coming after you, due to chance, he's getting service before you. This can happen when you have separate queues for separate servers. In this case, it may be that your line moves slowly because of the higher than expected service time of the customers before you, and the other lines move faster. And anyone who travels on the motorway would be a witness to this, because they have multiple toll booths and they have a dedicated line for every toll booth. And it is often the case that someone who comes later on is serviced before, and you're left waiting in your line, which is moving slower than usual. Another example of a multiple server queue is a call center. In a call center, again, they have finite number of servers, and every incoming customer is assigned to an operator. And when all the operators are tied up, then the future arrivals are queued. But this queue is again a single queue that feeds all of the operators. You don't have separate queues for separate operators. You can also think of multiple server systems in which no queues form, and this would still be a queuing system, because we consider customers in the system also in the purview of being in the queuing system. An example in this regard is the usage of telephone trunks, as was discussed in the example of Erlang. In this case, there are multiple servers. In this case, it would be multiple trunk lines. If you are lucky to come at a time when one of the trunk line is available, you would gain access to it. But if all the trunk lines are busy, then you would actually be lost from this system. And because of this, this system is known as a multiple server loss system, because there is no queuing. Either you would get the server or you would get out of the system. So lastly, we can also now talk of another kind of a queuing system in which we have infinite servers. And when we have infinite servers, again, we will never have queues build up, because whenever a customer comes, there is always a server available for servicing that customer. And because of this, this system is known as a delay system. So again, remember the last system in which the customers were lost when the servers are not available were known as loss systems, and this is known as a delay system because there are no queuing delays. The only delay is in servicing the customer. An example of this would be a private bank. Again, in a formal sense, we don't have infinite number of servers, but if we have enough number of servers, then you would never have a situation where a customer comes in and there will not be a customer service representative ready to service him. If you have that scenario, for practical purposes, we can imagine that we have infinite servers. And we can also use queuing theory to analyze such infinite server delay systems. It must be stressed that all real-life queuing systems have finite buffers, they have finite servers, and they have finite customer populations. But for the sake of analysis, we can often make these approximations and use calculations based on that, and often it does not make a big difference. And in fact, our default assumption in most queuing systems is that we have infinite number of buffers and we have infinite customer population. Based on these two premises, we can then assume that the arrival rate is a Poisson process, because a Poisson process is state independent. The rate remains the same. And also, if we have infinite buffers, what it actually means is that you will never have a situation where a customer would be lost from the system. Even if the queue is very long, we are assuming that the customer would wait and it would obtain service. Obviously, this is not always true, because we have situations where someone may leave the system after waiting for some time and they observe that the service is not forthcoming. But we ignore these conditions, and for the course that we are studying, we'd be assuming in most cases that we have infinite buffers and infinite source population unless stated otherwise. Okay, so now that we have specified all the different kinds and classes of queuing systems, we can now talk about the most popular notation used to characterize these queuing systems. And the most popular notation is known as the Kendall's notation, named after David Kendall, who proposed this. And this is notation in which we have 6 characteristics and they are separated by slashes. So you have 6 characters and they represent 6 different characteristics of the queuing system. Let me tell you about these 6 characteristics. The first 3 characteristics are the most important characteristics, and we always have to define these 3 characteristics. On the screen you can see this as A, S and M. So these are the arrival process distribution, the service time distribution, and the number of servers. So typically we have to describe the queue in at least these 3 terms, and for the remaining terms, even if we don't express them, we have some default assumptions. So what can arrival process distribution can be? We are actually modeling the inter-arrival time, and we are assuming that successive arrivals are independent and identically distributed. So these are IID random variables coming from the same distribution. So the only thing that now needs to be mentioned is what is that distribution. Typically, the most common assumption is the letter M, which represents a Poisson process, or the fact that the inter-arrival times are modeled by an exponential distribution. So this M represents memoryless property of the Poisson process and of the exponential distribution. This is also known as a Markovian queue. We can also have a D here, which represents deterministic arrivals. The term for the distribution from which we get deterministic times is known as a degenerate distribution, but you can actually associate D with deterministic times for your convenience. Thirdly, we can have the letter G in the arrival process distribution. This actually tells us that if we have a result for a queue in which the first letter is G, that actually tells us that this thing would work for an arbitrary distribution. Similarly, for the service time distribution, we have the same three characters, and obviously there are other distributions, but these are the most common distributions, and for the purpose of this course, we are going to focus on these. The third aspect is the number of servers. The most typical case is when you have a single server. The most typical kind of a queue is the MM1 queue, in which you have a Poisson arrival process, exponential service distribution, and a single server. But you can also have multiple servers. You can have finite number of servers, more than one, represented by M, or you can have infinite number of servers. So these are the three most important parts of Kendall's notation, and then we have three other characteristics: B, K, and SD. B is essentially the number of buffer space that you have to house both the service customer and the waiting customer. K in this sense is the customer population. Is it finite or is it infinite? Our default assumption is that it is infinite. Our default assumption regarding the amount of buffers that we have is also that they are infinite. And lastly, service discipline, we assume automatically that this is first in, first out, also known as first come, first served, but there can be other distributions. Let me now briefly show you the memoryless distribution and also the journal distribution, so that you have some intuition of how these distributions look like. If you have a memoryless distribution for the inter-arrival time or the service time, it would look something like this. And you also may note from our earlier sessions that the coefficient of variation, which is the same thing as the standard deviation divided by the mean of an exponential distribution, is 1. And we will use this measure to differentiate the memoryless distribution from the other distributions. A journal distribution is any arbitrary distribution. It can be an exponential distribution, for which case the coefficient of variation is 1. The COV value may actually be less than 1, in which case we would have a hypo-exponential distribution shown on the screen now. You can also have a hyper-exponential distribution in which the COV value is greater than 1. When you have the COV value less than 1, that actually tells us that the variance is small compared to the exponential distribution. When we have a hyper-exponential distribution, the variance is large compared to the exponential distribution. And if you have the coefficient of variation equal to 0, we have what is known as the deterministic or the degenerate distribution. In that case, we would be using the character D to represent that distribution. Okay, now let me show you very briefly two examples to demonstrate the Kendall's notation, and we would wrap up the session on this. The first thing is the MM1 queue. So if you see, we are only representing this queue by three characters: M, M, and 1. So the first character M is telling us that we have a Poisson arrival process. The second letter is telling us that we have an exponential service distribution, and the 1 is telling us that we have a single server. And for the queue scheduling, we assume FCFS automatically. We also assume infinite customer population and infinite buffers automatically. Other examples are of Kendall's notation, the MG1 queue, in which we have the Poisson arrivals, journal service distributions, and a single server, and the rest of things are the default assumptions. For a GG1 queue, we have a journal arrival process, a journal service distribution, and a single server. And lastly, if we characterize a queue by MM3/20/1500/LCFS, this tells us that we have a Poisson arrival process, an exponential service distribution, 3 servers, we have 20 buffers, so we can actually have 3 customers in queue and 17 waiting. We have a population of 1500 and scheduling discipline of last come, first served. Okay, now I'll be concluding this lecture and I'll be stating the salient points of this lecture. The first thing is we require the theory of the waiting lines or the queuing theory to study shared resources whenever we have stochastic arrivals and stochastic service patterns. Because in the case where we have a shared resource, even when the average arrival rate is less than the average service rate, queues would form. And because we want to analyze the performance of such systems, we should make use of the mathematics of queuing theory to derive performance metrics of this system. Also, one important thing is that queuing theory is by its nature only approximate, because we only have results when we can assume Poisson arrivals. For the other queues, we can state very less. But it already has been mentioned in this course that network traffic is not modeled very well by Poisson traffic. So what is the use of studying all of this then? The answer to that is queuing theory is useful because it provides us intuition and it gives us approximate answers. So with this, I end today's session. I'll see you next time. Assalamu alaikum wa rahmatullah.